Hello, this is video 45, and as you can tell by the already almost full whiteboard, I've been a busy little professor. I've already done a bunch of stuff so that you didn't have to suffer through seeing me draw it on the board, but you might want to pause a couple of times so you can get this down. This was the first thing. This is the starting point. This is just a picture of the graph we are trying to find. This is another example, by the way, of trying to find the shortest path from a starting node to every other node in a directed graph. And we realized last time, if we can do that for a weighted directed graph, we can also do it for the unweighted case and for the undirected case. So this is actually the most general solution. Here is the multicolor graph up here, and I'll read this off in case you can't read this stuff. But I'll just say what the arcs are. A to B is 3. A to D is 15, B to D is 7, B to E is 2, B to C is 5. Then from C to E is 1, C all the way back around to D is 6, D doesn't go anywhere. Everything's incoming to D. There's E to D with weight 4, E to C with weight 2. Last but not least, F to D is weight 3. F to E is weight 2. Now then, that's how we draw the picture so that we could get our mind around what this graph is, what it looks like. I don't know that we could draw it for a case of hundreds of nodes, but for smaller examples, it's a good idea to have the graph to refer to. Here is exactly the same information except represented as adjacency lists. Remember, this is the unbounded of the two, the bounded, the unbounded. This is the unbounded representation of a graph as a data structure that we might actually use in a computer program. And I realize some natural light is getting in the way there. There. Is that easier to read? But let me show you what I mean. It's the same information. Here's node A. This says from A, I could go to B with weight 3 or to D with weight 15. And sure enough, if I look at the graph, from A, I can go to B with weight 3 or to D with weight 15. How about B? B can either go to C with weight 5, or it can go to D with weight 7, or it can go to E with weight 2. Yada, yada, yada. C to E weight 1, C to D weight 6. D doesn't go anywhere. E to C weight 2, E to D weight 4, F to D weight 3, F to E weight 2. Why do I have both? Well, this was probably the one that's going to be handier for us to think about and refer to if we're actually trying to implement this algorithm. But I also wanted to contrast and compare. Maybe I shouldn't have used the same light blue color for the arrows, because these arrows up here actually represent arc connections in the graph. These arrows do not. These arrows just mean you're in the same data structure that I am, whether it's a linked list or an ordered list or standard template library vector, hint, hint, it could be that. But these blue arrows here, it looks like they're connecting C to D to E, but they are not. They are just putting all three of these together in a set that B could go to with just one step. B can go to C, or B can go to D, or B can go to E. There is no implication whatsoever that there is necessarily an arc connecting C and D. Is there? There is. That's not a good one. What about D and E? D and E. Yeah, there is no arc from D to E, so if you interpret the blue arrow that way, then that's going to be a misconception on the adjacency list. There, you've got all that. Now, all of that is set up so that we can start at a starting point, and the incoming arrow from nowhere up here means that we're going to start at A. But first of all, I haven't even run through what could probably be a constructor. And however I'm representing infinity, I can't even draw an 8 upright, but I'm going to try to draw a sideways 8 for infinity. Until further notice, we just assumed that every one of the nodes is an infinite distance from our starting point. And then we're going to try to bring it down to something finite and gradually make it better. Now, this is not a much larger graph. It's only got one more node. But I was careful to come up with a graph that does have some cases in it that were not explored in that 5-node graph. That was just kind of an intro to the algorithm in general. This one runs into other stuff that we're going to have to deal with, as you shall see. Okay, here we go. Let's start, shall we? We start by asking the user, where do you want to start? Let's start at node A, the user says. Well, how convenient for us, because that is our starting node. That means there. We now have one finite distance. A's distance to itself is 0. Your start node to itself is always going to be 0. You don't have to do any tests or ask the user or anything. So your starting point is always a 0 distance from itself. Now, let the iterations begin. What do we do at the beginning of the iteration? We find the smallest unfrozen distance. None of them are frozen at this point. The smallest unfrozen distance at this point is the only one that's not infinite. And then we freeze it. Freeze. I'm still using the same abbreviation. F-R-E-Z is freeze. Freeze A, comma. When we freeze A, freeze, we look to see if we can improve the distances that A can reach by a single arc. In other words, we are going to traverse. That sounds like a big, fancy, scary, recursive word from trees, doesn't it? But it's still used. We traverse the adjacency list of A. And look how handy this is to refer to down here. I could look at the picture, but the picture is kind of a tangled mess. Let's look at this. This is very organized. From A, I can go to B with one arc with the distance of 3. So what I'm going to do is I'm going to offer B my distance itself. That 0 is the distance to node A itself. Offer A's distance plus the additional distance it takes to get from A to B. Do you like that B? Is that better than the distance you already know about? Oh, of course it is. Yes, we'll take that. Check, please. 3. Now, this, remember, this is the variable trace here. It is not a two-dimensional array. Yeah, you get sick of hearing me say that in the last video, didn't you? This is kind of a repeat of the previous video, just with a different graph. But one of the other pieces of information we want to keep up with per node is what I was calling a crumb field. You know what? I'm not going to even label it as crumb all the time. I'll just put crumb up here. C-R-U-M-B. That's my name for it. What it is, it's like, where did I come up with that name? That doesn't even make any sense. It's like your trail of crumbs in the Hansel and Gretel story, how they're going to find their way back out of the woods. They leave a trail of breadcrumbs behind them. We're leaving a trail of breadcrumbs behind us. How did I get to B with a distance of only 3? I did that by coming through node A. So there's my crumb field right there. Bunch of stuff squashed into that node already. It's got a distance, the best distance it knows about so far. It knows whether or not it's frozen. That could be true or false. It also knows if there is a good distance here, it knows where it came from to get there. All of that was just for B. Let's do the same for D. I can also go from A to D with a weight of 15. That's a weight of 15 in addition to what it took me to get to A. The first number is the distance to the node that just now got frozen. You know what? This is going to make more sense once we get further down the road, but I've already started it. It's the distance that it takes to get to node A, which we're freezing, plus the additional distance on over to node D. From A to D is 15. Does D like the distance of 15? Absolutely. Check. We'll take that. 15. Also crumb of A. Anything that gets updated in this first iteration is going to have a crumb field set to A, because that's the only place we're looking right now to update nodes. Thus endeth the first iteration. And here cometh the first dotted line. Oh, I forgot. I was going to say freeze A and then the comma, update, UPDATE, the things in adjacency list. And look how handy it is to refer to that down here. B, D. There. Now am I caught up? I think so. What do we do at the beginning? The dotted line means, okay, let's go through our big loop again. A loop. This is an iterative algorithm. It's not recursive. We go through the loop again. Now, we ignore A. That's already frozen, so you're not even a candidate anymore. We look at the distances of the other nodes and find out the one that has the smallest distance that is not yet frozen. Why do we want the smallest one? Does it really matter? 3 and 15, they're not that different. Well, here's the deal. 3, that's the smallest one. We are not going to be able to improve upon that. How do we know? Well, if we were able to improve upon that, it would have to come through some other node in the graph, and no other node in the graph we can get to with a weight as small as 3. What about 15? Why not go ahead and freeze 15 instead of the 3? Well, 15, there could be a path that comes through B And then for 2 more, I'm not even looking, I don't know. 2 more, 3 more, maybe. Maybe we can get to D from B with a weight smaller than 15. So if we freeze this too soon, then that might not be the shortest distance from A over to D. Yeah, that's kind of jumping the gun just a little bit. Okay, just take my word for it. The next one we want to freeze is the smallest unfrozen distance, that's 3. Freeze that distance, no longer updated. We'll copy the crumb field down. Permanent distance, permanent crumb, freeze B. And who are we going to update? I'll list them before I get going over here. Update 3 of them, C, D, E. C, D, E. And remember, this adjacency list, this is a set. Did you know that there was a standard template library template called set? I don't know that that would be a good one to use here. I take that back. Vector is probably better if you're searching around for a template to use. But anyway, here we are at B. We've got to update CDE one at a time. We offer them distances. Now then, update C. Let's do that first. B to C. The distance we offer from B to C is this, 3, not the 0 anymore. We're not at still node A. This is the distance over to node B, the one that we're freezing, plus the additional distance over to C, that's 5 more. 3 plus 5 equals 8. Well, I didn't put equals up there, so I'll just say, do you like this better? 3 plus 5, do you like that better than infinity? Yes, we do, of course. 8. With a crumb field of B. The crumb field is who we are freezing right now. That's one way to think of it. It's also the next step backwards if I'm going in reverse along the shortest path that I know about so far back to the start node. Stop talking and keep writing. B to D, right here, we offer plus 7. 3, the distance to B, plus 7, the additional leap over to D. How's that look? Now look, this is an example of what I was talking about that didn't show up in the last graph. This is not infinite. This knows about a path of length 15 over to D from the starting point. But look, we're offering it an improvement. Is this better for you? Yes, we'll take that. You are out of here. 15 is no longer the shortest path we know about. We now know about one that's 10 coming through B. You see what happened there? I mean, this algorithm has so many pieces to it. It is kind of challenging to come up with a small graph that exposes all the different things that can happen. There's one of the things that can happen. This got updated twice already. We're just now getting going. What else? From B over to E, weight 2. Yeah, we're almost certainly going to take that, right? 3 plus 2. Do you like that node E? Yes. Yes, in fact, I do. So I'm not marking out the infinity. I don't know why, but it's not infinite anymore. You aren't, you aren't, you aren't. 3 plus 2, that's 5. From crumb node B. That looks like a D with a bump on it. It's supposed to be a B. It's even worse, but it's a B. And we've updated all of them. We've gone through the entire adjacency list. End of iteration. At each iteration, we only freeze, we only permanently mark as the best one node per iteration. That's the limit. So we're going to have to at least go through enough iterations to check and make sure that all the reachable nodes get frozen eventually. Who's next? Well, we don't consider the 0, we don't consider the 3. Those are marked frozen in the node field over here in the array or vector of nodes. All this stuff, by the way, this chart or table or whatever you want to think of it, that's stored in this stuff over here. The arcs don't change as we're running the program, but these node structures do. Their distances are going to be updated. They're going to be marked as frozen or unfrozen. So there's a lot going on in this little stack of A, B, C, D, E, F over here. Who's next? Looks like E. Freeze E. Update. Whoever's in these adjacency list. C and D. Okay, well, first of all, I need to freeze E. E has distance 5. That because I did a search. I went through this array. This is an array or a vector. I went through this a one-way trip and found out, you know what? That's the smallest distance that's not frozen yet. So now it's its turn to freeze at the top of this iteration. Its crumb is B. That's also never going to change from this point forward now that it's frozen. Let's update C. The distance to E was 5. So I'm going to start with that. 5 plus something. The additional distance from E over to C is 2. 5 plus 2. How you like them apples, node C? Well, I like them pretty much. Thank you very much, node E. 5 plus 2 is 7. That's better. Look again. Oh, we update again. We update this from 8 to 7 with a crumb field of whoever's getting frozen, E. Check. Yes, we like that. You're out. 8 was pretty good. 7 is pretty better. From E to D, E to D, 5 plus something, E to D. 5 plus 4. How about that, D? You like that? Yes, D likes that. That is 9. That's less than 10. So 9 is now the shortest distance I know to node D from the starting point with this new updated crumb field of E. So far, so good? Is everything set? I didn't mark that out. Look at this. Look what's happening here. This started off an infinite distance away. We found a path that was 15 away, then a path that's 10 away, then a path that's 9 away. You know what? This could be updated even still. Until it's frozen, there's always the chance that we'll find an even better, shorter path to that node. When it's frozen, we know we're not going to do any better. Who gets frozen next? Well, we look at all the ones that are not frozen. We're running out of unfrozens, but it looks like the 7. 7 is going to get froze with node E as its crumb field, and 7 is node C. Free C. Update whoever just needs to just your list. E and D. Well, here we go. 7 is the distance over to C. The additional distance from C over to E is 1. That sounds pretty good. 7 plus 1, that's not very much. So we're going to offer that to E, but look. It's not even going to look at the offer. Already frozen. A-L-R-E-A-D-Y. F-R-O-Z-E-N. Now, of course, you're not going to represent that in your program, but the reason I'm not writing something new in this column is once that distance gets frozen, it shall not be improved upon. We know that for reasons previously explained ad nauseum. So that's already a frozen, exclamation point. So we're not going to be able to offer that anything. It's going to like it wouldn't take it anyway. It would be what? 7 plus 1, 8. 8's not better than 5. So it's not going to accept that. What about D? D's not frozen yet. So E is 7 plus the distance from C to D is 6. 7 plus 6 is 13. So we offer D a distance of 13. How do you like that? You know what? D doesn't like that. 13 is not better. That's not an improvement. It already knows about a path shorter than 13 from an earlier iteration. So the answer to this is no, X. That's the first one we've seen that did not accept an update offer. You don't necessarily update the node every time. You only update it if it's better than what you already know. So both of these, look at this. Poor C couldn't find any customers at all. E rejected the offer because it was already frozen. We don't even give it an offer. We don't even ask. C to D, we did offer that. How do you like 7, the distance to C, plus the 6 additional over to D from C? It didn't like that because it already knew of a shorter path. So already, all kind of cases all over the place. And I'm covering just about all the cases I know about. So maybe we'll run out. That was freezing C, and we've given everybody a chance. That's the end of the iteration. It goes back through, and as long as what? Well, how long do we keep iterating? As long as there are unfrozen distances that are less than infinity. As long as there are unfrozen distances that are not infinite. Are there any? Well, we have to search for it a little bit, but this is the most recent update to D, so that one's going to get frozen. Actually, that's the only one, so it is absolutely the smallest unfrozen distance. Its crumb field is E. So what am I doing? I'm freezing D. Freeze D. Update. Nobody. Update none. I don't think we've seen that case either, where there was not any additional work to do. So that's the end of that iteration. Next. Well, there is no next, because all the ones that are less than infinity are frozen. I'm sorry. I just now realized that it's the last column again. There is nothing magic about the last column. It's not, in general, going to be the case that all the frozen ones come before any of the unfrozen ones. That's not, in general, going to happen. Let's pretend C could have been. If I switch C and F, if I have to redo this video because it crashes or whatever, then I'll make sure to do that. But here's where we are. We've frozen all of the distances that are less than infinity. So that is the shortest distance. You know what? I'll put a box on there. There. It looks like a mask. That's the shortest distance we know about from F, which actually implies that F is unreachable from the starting point. And a quick look at the graph will reveal that, in fact, it is. Even though F does have an adjacency list, F doesn't show up in anybody's adjacency list. Nobody can get to F. You can't tell that at a glance necessarily in your code, but in the graph, sometimes that's easy to spot. Well, what new things have we seen? It's possible that the shortest distance will be updated several times before it eventually gets frozen. Be sure you always freeze only the one node that has the smallest. There could be a tie. If there's a tie, it doesn't matter which one you freeze next. But one that's less than or equal to every other unfrozen distance in the graph. What else? Already frozen. We don't make any offers. This has all kinds of cases in it. Watch it carefully. Take good, solid, complete notes. Think about it real hard. And if you have questions, see me during office hours or make an appointment, and I'll see you online.